Okay, so maybe we'll get started. Good afternoon. My name is Ichiro Takeuchi. I'm the interim chair of Department of Material Science and Engineering here at the University of Maryland. Together with the Department of Mechanical Engineering, we would like to welcome you to the fourth George Dieter Distinguished Lecture Series in Mechanics and Materials. First, I'd like to acknowledge those who made this lecture possible, including our donors, staff, and faculty members in both departments. I would also like to acknowledge some of our guests who were supposed to actually join us through Zoom, but Zoom is down apparently. So Carol Joan Dieter, George Dieter's daughter, she was supposed to be online, but she couldn't join us. And also J.C. Zhao, our former chair, was supposed to join via Zoom, but well, he was also busy anyway, I guess. But we have in person, all of you. We have a few alums, including Prasan Somal. Thanks for coming. And we have members of the ASM Washington, D.C. chapter, right? Are you here? All right, thanks for coming. Let's see, as some of you know, George Dieter was a prominent scholar in the fields of mechanics and materials and served as the dean of our college between 1977 to 94, setting a path of growth for our programs. Close to his passing in 2020, President Darrell Pines made way for a collaborative effort between the two departments that would honor his lasting contributions to the college. So as a dean, George came to the university with a vision to turn this, what used to be Glenn L. Martin Institute of Technology, into a standalone school and college, and left having cemented some of the most foundational changes, including the launch of the Maryland Technology Enterprise Institute, the Institute for Systems Research, the Gesell Rotorcraft Center, the Center for Minorities in Science and Engineering, and the Women in Engineering program. Some of his academic accomplishments include his induction to the National Academy of Engineering in '93, and authoring the textbook Engineering Design, which many of us are familiar with, which serves as the foundation of the capstone design curriculum in many engineering departments. His other book, Mechanical Metallurgy, is considered a Bible in the field of metallurgy and materials engineering. And both of these books live on the shelves of many engineers around the world. So in our efforts to continue his commitment to creative research, please welcome Dean of the A. James Clark School of Engineering and Nariman Forwarding Professor Samuel Graham Jr., who will introduce a distinguished speaker.
Thank you, Ichiro, and good afternoon, everyone. It's my pleasure to be here today for the George Dieter Distinguished Lecture Series. This is, don't tell everyone, but this is my favorite one of the year. Always enjoy coming to this one because of the opportunity to meet such distinguished people in our field with the presentations and the interactions that we have here in the Clark School with our guests. When I think about what we do here at the Clark School as engineers, we are really driven by the seeking out new knowledge, understanding how our systems work, solving problems, and translating those solutions to industry or to society in order to improve the lives of others. And one of the things that we have the opportunity to do through lecture series is have the opportunity to have exchange and to learn, take a break from what we're doing in our busy schedules in the laboratory and come and convene and actually have a discussion on important topics to learn about some of the advancements and how we arrived at those through the guests that come for this lecture series. We're fortunate to draw high caliber speakers for the George Dieter Distinguished Lecture Series. Previous speakers, for those of you that have come every year like I have, included Mary Boyce from Columbia University, William Nix from Stanford University, and John Hutchinson from Harvard, an outstanding group of speakers. Today's speaker is in the same category as those other three. So I'm excited to introduce Dr. Tresa Pollock from the University of California, Santa Barbara today. She has devoted her career to the discovery of new materials, as well as the application of those materials into important engineering problems. She was elected to the U.S. National Academy of Engineering and the German Academy of Sciences, Leopoldina, as a result of her achievements. Her research focuses on mechanical and environmental performance of materials in extreme environments, unique high-temperature materials processing paths, ultra-fast laser material interactions, alloy design, and 3D material characterization. She worked at the General Electric Aircraft Engine Company from 1989 to 91, where she developed high-temperature alloys for aircraft turbines, and she co-developed the single crystal alloy renamed N6, which is now in service. Today, she is the Alcoa Distinguished Professor of Materials at the University of California, Santa Barbara. Please take the opportunity with me to welcome Dr. Tresa Pollock.
So thank you, Sam, for that very kind introduction. And I'd like to thank the Department of Material Science and Engineering for being such wonderful hosts. I've really enjoyed the day greatly. So today I want to talk a little bit about exploration, and of course that will be with regard to materials, but maybe a little bit more generally at points. And so we're all scientists. I think we all are curious. We'd like to see every corner of the world. I am personally upset that I can't go to New Zealand for the weekend yet. Requires a flight that is maybe at slightly higher speeds than we have available now. And certainly breaking the sound barrier is not a straightforward thing from either a mechanical engineering or a materials perspective. Perhaps some of you students someday, let's see if we can get the pointer right, we'll even have the opportunity to take a hike on another planet. And yes, this is AI generated. I had a lot of fun making it. You know, we've always had a tendency as an engineering community to celebrate the explorers. And so I don't have to tell you who people on this screen are. I think we all know them by sight. But I think what we don't celebrate enough is the people who actually made that possible. And so this is Maxime Faget, and he designed the Mercury capsule as well as had a key role in the Gemini and the Apollo and the space shuttle, and yet very few of us know who this is. And so it's, I think, very important to recognize what makes exploration possible. And of course, he is an immigrant, but was educated in the US. And I also think we don't spend enough time celebrating some of the giants of our field from the education point of view. And certainly George Dieter was one of those people. And I did actually know George, mostly because we had this Carnegie Mellon connection. Many people do their time there. George did, I did. And so for that reason, I met him. And I love this photo of him because it really brings back to me what I always thought was so wonderful about George, which was he just loved being a faculty member, building things, teaching students, writing books. This, by the way, is my favorite book. Not only did I learn from it, in the early days I actually taught from it. And I think one day I asked George how he came up with all the good homework problems. I always found that hard to do as a young faculty member. He's like, oh, I always sat on the beach and wrote those. So I don't know, maybe he did. Okay, so just a few things about extreme environments. I think you already see where I'm going with this. We're thinking about things like aircraft engines, rockets, where we have very high temperatures, very high pressures, and certainly lots of challenges with regard to materials. And here's just a recent example, the SpaceX Falcon Heavy. What could possibly go wrong if you have 27 engines taking you somewhere? Nothing, right? But I do want to talk about some of the challenges with regard to materials and how they enable these systems to work. Some of the things that we really have to think much harder about to get to New Zealand. Now, you see those temperatures and pressures, and you think, well, obviously the thing I want to do is go to the chart of materials, and I see I've lost a caption there. This is melting point. Oh, it's of various classes of materials. sulfides, nitrides, fluorides, refractory metals. And you would want to think that, well, the easiest thing to do is just go up to the top right and pick the carbides and put them in these systems, and then we're set because they have a high resistance to melting. But of course, that's not what we do, and those are not the materials we use. And so I'll talk a little bit about some of the materials further down this chart and why it is those are the ones that end up being useful. And the real reason is that, of course, when you pick a material to serve in an engineering component, it has to satisfy lots of requirements, not just one, like the melting. And so the Space Shuttle main engine was sort of an interesting exercise in the first time having to find high temperature materials that were also very resistant to burning. Here's an example of one set of materials that didn't go well. What was the Rockwell Science Center. The other thing you have to do is worry a lot about failures and making sure that failures don't occur. And so this, strangely enough, is my favorite failure. This is an American Airlines Boeing 767 landing at LAX in 2006. And the first stage turbine disc in the pressure part of the engine underwent an uncontained failure. And you can see, I don't know where to point, but you can see what happened is the plane landed, they took all the passengers off, there had been some vibrations of somewhere, they ran the engine back up to full power, and the disc from one engine actually got loose, bounced under the plane, and took out the second engine. And so, fortunately, all the people were off the plane, but the question is, how do you find and guarantee that these materials are damage tolerant enough that we can trust ourselves to send people to space or across the Earth? And so when you think about it, the set of materials available is not expensive. And so the question is, well, why is finding new materials so hard? And so from the point of view of the materials, some of it's availability. There's things we'd like to use, but there's just not enough of it on the Earth. We have to manufacture things into complex forms. We have to get a whole series, a suite of properties. And so I show here an important point. This might be a full set of properties that you need for a material in an aircraft engine, for example. And some of them are pretty straightforward. Density, melting temperature. I can measure these things and know what to expect. But as we get up here into things like fatigue and ductility, it becomes much, much harder to predict. And the volume element that really sets the property becomes larger and larger. So we have to sort of get to the point where we know everything about at least a cubic millimeter of material to predict something about fatigue. And so all of these things combined with the choices on the periodic table, obviously the parameter space is very large. And then on the performance side, there's also another enormous set of parameters. You don't really know what will happen. This photo here on the cover of Advanced Materials was taken by a good friend of mine, Peter Green, who was at that time a senior pilot at Delta Airlines, flying past this volcano the day it was erupting. I was quizzing him about why he was so close, and he just claimed he had a really good lens. So anyway, you don't fly airplanes near volcanoes because all of that ash will deposit and cause things to melt. So there's all these uncertainties about the environment, stresses, temperatures, volcanoes. We have coatings, and so the complexity of the systems is also large. And so again, there's a lot of things to take care of. And so how do we find our way forward toward new materials, given how large the parameter space is for an engineering material. And so there are things we need to do. Materials, we have data, but maybe not lots of it, never enough of it. So as a community, we can be doing more about rapid characterization and autonomous synthesis and things of that sort. And I'll talk a little bit about that in a few minutes. We need better models always, high fidelity physics models. Computational power is increased dramatically in the last decade, and so we need to leverage that. Then we have this new question about AI and ML, and I'll make a few comments about that as I go along. Now, I think probably everyone in this room knows that nearly all inorganic materials are polycrystals, and we tend to have this view in our mind of what they look like in 3D. I'll say that we've done lots of work in 3D that I'll show you in a moment, but this is one simple data set of a strontium technate, and all the things that you've been taught in your textbook about how many neighbors this brain should have are not quite true. And so there's so many things about brain boundaries themselves that affect the properties of materials that we still need to better characterize and understand them. Or you could go the way that we did in aircraft engines, and this is a bit of a historical comparison to the way things are done now. So this goes back to my days at GE, where I was told, make a new turbine blade material, and it will be a single. And these materials are made primarily of nickel. Most of the aircraft engine by weight is actually composed of nickel alloys. We need to understand them in great detail. And so the question was, can you find a new material to do this? And so in these days, this is what we were forced to do. You don't need to look at these numbers in detail, but I don't think I did that. Okay. So if you look at this, these compositions of years of 34 alloys, this is the way you had to do it. This is the way we were ordered to do it. In fact, you make up a design of experiments, you go off, and you make single crystals 34 times, and then you finally come up with an alloy. In this case, composition X1, and there's a whole bunch of rhenium in it, and we thought that was great. Business of growing single crystals is very expensive, very slow. We're growing these single crystals out of the furnace an hour. So this is not a fast process. And everyone, of course, knew that it was not only not a fast process, but what often happens when we get to the end is something that's wrong. So after all those rounds of just a little bit of screening, then you're told, Tresa, make a turbine blade. And I don't think I have to explain to any of you that that's not. And so what we have here, pegs, which are small chains, equiax triangle grains that will issue cracks into an engine, and that's one big problem. And the second thing was, oh, we need coatings, and so we put on a coating that we expect, and then all of these things come tumbling out. And so the idea is to get closer to predicting these things before you ever even make the single crystal. So as computational powers improved, in this particular problem, we spent a lot of time getting 3D data, doing modeling of fluid flow through the dendritic array in order to understand convection in the melt. And that is because these convection processes are actually what cause hot fluid to come back to the tips of these dendrites and separate pieces off, which become high angle grains. And so we're now to the point where we can do those sorts of calculations before we have to find out the hard way that it's going to be impossible to solidify something. And then on the coding side, again, that was a setback that cost a year or so. And the point is that when you're using materials at high temperatures, you often don't have the luxury of just having one material. You need layers of materials for various functions. And so the way it works in these systems, you have that single crystal down here, and you put an intermetallic on code whose function is to form a protective layer of alumina, hopefully without too much diffusion. And then on top of it, you put a porous Nigetria stabilized zirconia thermal barrier coating so that you can have, it has very low conductivity, and you can run hot gases across the surface of the blade that actually exceed the melting temperature of the substrate. And so this, of course, gave lots of benefit and efficiency. But the problem is that you have to make an intermetallic stick to the metals and stick to a ceramic with an oxide in between. And so, again, the parameter space is large. How do you pick the properties of each of those layers so that you can thermally cycle the system and it won't fall apart? And so there are many different ways that these coatings can fall apart. And I show here a plot that we lived by for an effort that was led by Tony Evans, where we sort of marched through looking at turbine blades, modeling, making models for all these different modes of degradation that the coatings would have. And so where does that come in handy? Well, years later, when we have identified some new alloys for 3D printing, then in a few hours, we can go and ask which ones are most like our conventional materials, then have confidence that the driving force for the failure of the coatings layers will be, so that we can put that problem to rest in the beginning instead of being surprised at the end. And so what are these alloys? I think everyone here knows that 3D printing, there's been a lot of excitement about it. And if you go and look at, say, the GE website, what powder will they sell you to put in your 3D printing machine? There's about 10 alloys. You know, in normal circumstances, you usually get to choose from, let's say, 5,000. And so the question is, can we put together sets of tools that allow us to march through composition space and find materials that have suitable properties? And I won't belabor the point other than to say it certainly takes a lot of effort to build these kinds of models and rapid characterization, but in the end, it actually helps from the point of view that we finally found a very printable material, which is precipitation strengthened in a way that no other printable materials is, and then even has a lot of ductility in the as printed condition across electron beam or laser powder bed processes. And so continuing to build the infrastructure is what we need to do to find these new materials. Now here I make a transition. And this is refractory alloys, and specifically refractory multi-principal element alloys. And the idea here is that, of course, in the 1970s, there was a lot of work developing refractory alloys in the days of MASP and programs like that, and almost nothing since then. And then along came this idea that you could, if you could take high concentrations of mixtures of 3, 4, 5 elements and mix them in equal atomic amounts, that the material may not know what its base material, what its base element is. Therefore, you may be able to may be able to sort of trick the material into not knowing what its weaknesses are in effect. So can you find new behaviors in refractory alloys in this high dimensional composition space? The thought is, you better be able to use them at 1300 C or more, or it probably won't be worth the effort. So there were some early things from the Air Force that were very promising, and so we jumped in to see if we could find anything. Now, one might think, ML's come along, let's make a database and find some materials that way. And so we did, and used some random forest decision trees to try to make the recommendations from the many thousands of predictions. And I'll be honest, this was not very useful. It was interesting, but not very useful. And the reason was that almost everybody was doing work in the same area, so there wasn't enough data, particularly in wide composition spaces. And so I think the point is, if we're going to pretend that we're going to do a lot of ML, we'd better also make sure that we have some data to do it with. Now, the real challenge with these systems is that they have melting points above 3000 C, and you have to go from, if you're going to melt them, which you usually do if you make something, you have to go from 3000 C down to room temperature. And so that means you have some solidification path that you're going to follow. And usually what it means is that the highest melting point thing in the alloy will come up first, and the composition will evolve, and maybe other phases will come about. And this is, you see the scale here, 20 microns. This is clearly a mess, because you will never be able to homogenize this. And it's not going anywhere. So again, you have to think about some higher throughput tools in order to decide whether or not any of these things might be worth going after. And so the first thing that we did was develop this flat tinting approach so that we could have very uniform composition that you would ultimately get if you really worked hard on an industrial process, and really just sort of assessed how ductile things were by getting these little mandrels. And so a lot of searching there, combined with doing some screening with thermocalc, and the realization that we needed higher temperature materials that almost inevitably requires precipitation. So I don't have time to talk about those, but a whole screening methodology that brought us to PCC analogs, which are continuous matrices with E2 order precipitates that do the things that we always want them to do: inhibit dislocation motion, formation of boron loops, and have high strength above 1200. I guess I probably won't show you a lot of the compositions. I will say that this particular material, I'm sorry, I didn't get the font changed here, but it is ruthenium titanium in two phase. And so while very strong, maybe not so practical, but it does point the way to some other compositions. So again, to get to using these materials, the reason there's a lot of excitement at the moment is that 3D printing now gives a new way of making these materials that have high cooling rates so that we don't suffer impurity if that's the application path. And so then the question becomes, well, what are the approaches that we're going to need to really make finding a 3D printable refractory alloy possible? And so I don't know how many people in the room own the printer. I do. So we affectionately call a 2D printer. Same optics, same laser, but a nice little chamber that we can control the gases and we use this now to do additional sweep on layered materials for plasma sintering system. The idea is to just do some simple line melting experiments. If they crack by solid state or by solidification, put together some fracture mechanics models, and then criteria for alloys in the no cracking, solidification cracking, or solid cracking domain, so that we can look at that before we ever think about going to make powder that'll probably be $10,000 a pound. So, and again, just like our conventional alloy supply now, we need coatings. Most of these materials have terrible oxidation resistance. Now we have more tools, A analysis and Python generated compositions, space, and classify materials into different classes so that you can make sure that the experiments you're doing are on different materials. And then by scanning photo activity and melting, we have found coatings which are formers that survive up to 100 C and will provide some protection for these materials. So again, the message is building the tool set for getting there. Okay, so the last sort of tool set I want to talk about has to do with structure, right? All materials know that the microstructure of the material is critically important, and this is one of my favorite plots. This is just pure tantalum, and the added and if you go and do high-rate deformation experiments, the strength of these two materials just for pure tantalum. That's all just microstructure. So I think if we're really going to do 3D printing, we might need to really understand. So this has motivated something that we've been doing for probably the last 15 years, and it's this development of a platform that we refer to as beam microscope. And so this is basically a focused ion beam microscope. In this case, it's a Versa 3D from Fisher. That would, of course, have an electron beam, an ion beam, and then we have taken into this chamber of just second laser. You can see all the beams here, very crowded scope. And the motivation for the femtosecond laser is to basically give us a very high throughput way of slicing large amounts of material at the resolution you need to get multimodal microstructural data. And so the way that it works is shown here. So we take a sample. Second laser glancing incidence, and we scan the surface, remove a layer that's anywhere from 100 nanometers to micron, if you wish, and we just do that sequentially over and over. And so what you're seeing here, what you're seeing here is one of these. What you're seeing here is a movie showing layers. You can see some so why femtosecond? You late material, picoseconds, radiation is constant. And so if you have a pulse that's longer than that, as you ablate material, it wants to pump energy back in, the ablated material, and then deposit it. That would be melted. When you have femtosecond pulses, the laser's off, the material leaves, and so you get these very high quality surfaces after the ablation by backscattered detectors or EBSD, and so you have a way of getting this multimodal data as you tilt around in the microscope. So this is sort of a typical workflow, and the real benefit of the femtosecond laser beyond not doing any collateral damage is that it's really fast. So if anyone's ever tried to make a FIB data set once, you're able to make a slice in 25 seconds. And then the slow steps are some of the analysis that comes with it. So we are working on making these things faster. This part is now very fast. And the other interesting thing about femtosecond pulses is basically everything has a completion threshold, not so different from one material to the next. And what it means is that this approach is pretty much materials blind. So you can increase data sets on metals, ceramics, alkaline, very dense. They would have trouble imaging in the synchrotron. And so we've been working on this for many years, collaborating with Thermo Fisher, and finally got to the point where we sort of made a lot of design input, and now there's a real commercial system. So we've installed this in the last couple of weeks. We wrote a complete software interface for them. You're welcome. And if you buy this system, we'd love to have more friends making 3D data. Okay, so I just want to show one application of that 3D data. Back to that turbine disk that failed in the turbine plane. And so the material is interface by superplastic processes that start with powder materials. And then a few things. There's this feature of the structure that develops during processing, special low-angle boundary twins. I'll come back to the wire, point that out, and then very little crystallographic texture. Certainly, nickel has a very high elastic anisotropy. Oh, sorry. The other thing is you do fatigue experiments on this material out to the billion cycles here. What you see is that as you get to lower and lower stresses, closer and closer to where the material operates in service, the scatter in the fatigue actually becomes much, much higher. That's a little disturbing, and so the question is why? And so we've made a number of data sets of these materials, various different resolutions. This is probably the material we have the most data on. And if you look at these red-blue regions, these are grains, but they, during recrystallization, develop these annealing twins. It turns out they play an important role, and those are the sorts of things that you can image in the system. And so to give you some sense of the population of those special twin boundaries, all the blue ones are the twin boundaries, and all the other colors are regular Hyman boundaries. And if you, this is kind of a mess. My computer scientist friends tell me, we can't really, we think we can see materials, but we can't really. And so this is from this data set, all of the places, all the triple junctions in the material, all the places where 3 grains come together. It turns out those are. Now I'll show you a few things that we've done using the heavy side digital image correlation. I think everyone knows what digital image correlation is. The only difference with the heavy side is that it can detect a localization event and then split the problem apart and use a heavy side analysis so that I can now know exactly how much slip happened in this band. And so regular DIC would give you these points, and the heavy side would give you these. So I know exactly what the displacement is along the slip band, and then I can observe if those things the number of dissipations come by. And so this shows you some of the hepcided mapping. We have strains here, and grains that are going down. Does not happen to the following pepper. And these are the placement amplitudes within those same grains. And so you can see here we have some that are in the vicinity of about 6 nanometers. That probably means we've got about 250 dissipations pass down that slope. And this is after 1.26 percent deformation. The resolution is about 10 nanometers. And now what you're seeing here, flashing back and forth, is this sample image after loading and tension, and that's the one with a lot of slip, and then loading back. So if everything were completely reversible, I should get back to zero, right? Because this is macroscopically what I did. But of course, that's not what happens. If you look at the highest displacements here, they're at 130 nanometers. And so there's this grain in the center where you get this very intense slip that really doesn't reverse. And so there are specific regions in the structure, and they're always a little bit offset from these twin boundaries. And the mechanics are such that we have a stress concentration near there. We have very few pre-existing dissipations and slip events near there, and in some cases they are not reversible. And to show an interrupted experiment, let's see, there's this band after the first cycle that has very intense slip, almost nothing else in the view, and this is where the crack initiates many hundreds of thousands of cycles later. So that's interesting. After one cycle, we might be able to detect where the damage is happening. And so with 3D data sets, we can not only know what's going on at the surface, but what's going on underneath me. And so a couple of my postdocs spent a lot of time writing software to merge all of the data, correcting for all the distortions of the microscope and so forth, and superimposing the slip bands on the 3D microstructure. And so it turns out there's a number of important configurations, these places near the twin boundaries, and even more important if these twin boundaries are near a triple junction where all the grains come together. So where all the constraint is the highest in this elastically anisotropic material. And so then we can classify them by the kind of junctions they are, and we find that these most intense ones really are the places where we have those twins near the triple junctions. So it's a little bit like finding the needle in the haystack. And so, but at the end of the day, this does give us a rapid way of thinking about materials, because here we have a whole bunch of different materials, nickel, titanium, copper. We've since done a few more than this. You can see they're all loaded at different temperatures. They have grain sizes, different states of precipitation, different R ratios during loading. And what you can see is if you plot fatigue strength as a function of, this is fatigue strength at 10 to the 9 cycles, a billion cycles, normalized by the yield stress of the material. And this is the slip localization amplitude after that first cycle. So where did you see the first intense slip? And this is a linear relationship. So what it tells us is that if we can look at those very early features, rare features of the material that cause localization, then we should be able to predict what the fatigue life is at a billion cycles. So an interesting outcome of a combination of these. So I will finish by just saying a few words a bit about AI and ML. In some places, like I said earlier, not very useful. When you start dealing with 3D data, there are places where it is very useful. And these are mostly in the area of vision. So just algorithms, constructing data sets, bands, making synthetic microstructures that are represented data sets, UNets for detecting flaws in the additively manufactured material, and graphs. So you basically, in this case, put a node at the center of the grain. We can use these for propagation. And most recently, we've been trying to do some things with LLMs back to this problem of refractory alloys. It's getting more hopeful. And so things develop, they go slowly, but I think in the end there will be places for AI and ML, but we have to think carefully about where they'll be useful. So I just want to finish by thanking my own explorers. This is my research group. You've seen their work in the slides before you on a typical day in Santa Barbara. Nice place, come visit. And I'll end here with just a few final thoughts. So developing materials for extreme environments, challenging task, requires optimization around multiple objectives, properties. We need tools to think about those objectives and properties, and we need both characterization as well as modeling tools. I think AI and ML will help. Autonomy will also help, but this is early days for those sorts of things. It is running our microscope. So with that, thank you very much, and I'll be happy to take some questions.
Oh, yeah, yeah, yeah.
Nice talk. I was wondering, in the refractory materials, so this is way back at the beginning of the class, of the talk. You were talking about making a mix so that you could get them more uniform. How large must the
Right.
all the way? Yes, all the way.
All right, just ask, I'll keep going, but
How large must that uh, region be such that you won't touch it? No, it's way back.
So,
Uh,
I'm not
you,
sure I understand.
no.
how
How
large-
large must the region be such that it won't further? Uh, yeah.
Oh, these are just tiny samples, about diameter of a quarter, about
Mhm.
50 microns thick. So you really have to have basically took a conventional sweat punch system and amped it up, both with TZM and copper tungsten, so that we survive these very high temperature materials. So it's not enough material to do much of anything with. You could sample, you could make some small micro tensile samples. We took some strips out here and sent them off to our friends at Johns Hopkins who measured melting temperatures for some of these materials, and things like melting temperatures we don't know. And so there's a lot you can do with a little bit of material, but it's obviously.
So you cannot get at the point where you have to say we have to stop here because then you will do uh, the material won't fit what you are looking.
No, I mean, if you can't make it this way, you're never going to make it any other way, for sure. So some of these would be very brittle, and when we spot them, be fall into pieces. So that's not going to work. The idea here is that this is very rapid cooling, and so that would sort of be consistent with how rapid the cooling is in 3D printing. And so if you can survive this, then maybe it's worth taking the next step to maybe ultrasonically atomize some material and try the technique, for example. So having a whole series of things. All of these elements are expensive. Yeah, just we need something at every step of the way to let us know if it's worth continuing on. Is sort of the way we think about it.
Very nice talk. So when the grains grow for each layer, So you have the same orientation maintaining.
In the additive data sets?
Yeah, in the
That's further back, I think. So we have done a lot of work on that. I didn't talk about any of it. For example, that data set that we showed, right. So in the data set that I showed with the cobalt, sorry for making these switches. Um, Most of those brains would propagate through 10 or more years, even with a bidirectional. And um, when they undergo these bidirectional changes in scan direction, and the material wants to follow the beam. And so what happens is that you get tremendous amounts of rotation and misorientation inside these grains. And so then we can, from those, because we have 3D data, we can measure GMD density that is induced by the printing process. So the GMD density to accommodate all of this violent rotation induced by the printing is constant per layer and accommodates a disorientation of about 0.7 per layer as you continue to print.
Is it possible to start with a seed crystal and maintain the same orientation so that somewhat similar to the unidirectional certificate?
Yes, it is possible. We haven't been trying to do that, but I spent decades growing single crystals, so yeah, I can do that.
Yeah,
I
thank you.
haven't, but it hasn't been in the mission lately.
We're going to ask the students now.
Fantastic. I found your work on fatigue imaging fascinating. And you were able to, after the first cycle, identify critical slip lane. And I assume that you check to see if it has the highest critically resolved shear stress.
Oh yeah, it has a lot more than that. So it, because in this particular case, we've taken like two scans and said, oh, we think these are the potential initiation sites. And that was on the basis of high Schmidt factor, twins, killing twins in the right orientation, largest grains because they're on the high tail end of the distribution. And if you apply all of those criteria to like a 2D surface, still doesn't quite tell you what the needle in the haystack is. And the thing that goes along with that is the fact that if you really think carefully about fatigue here, I've got a gauge diameter that's a couple millimeters, and if that were the RVE, if you will, then it would variability. The feature is even rarer. And so beyond those obvious first few things, what turned out to be true is these additional that you have annealing twin which intersects a triple junction. So it's sort of like the superposition of two things that will give you a stress tensor. And this is more consistent with the volume of material that you're encountering.
So is the microcrack initiated at the triple junctions?
Yeah,
Is that
so
where failure occurs?
yeah, so here's an example of a microcrack that originates with triple junction. Here's one that cracks are really dark. There's one that initiates at a twin boundary, and when these things are simultaneously true, that's when the highest. We have those 3D data sets, so we can go and project where the high amplitude events on the surface were into the depth. And then by projecting them into the depth on the 3D data sets, that's how you find these, not very good, and these kind of events. So it's the combination that fix it. allowed us to find the more rare aspects of those irreversible slip events. And that I have to credit a couple of my postdoctorals. All the code got written during the pandemic because they didn't have anything else to do. I don't know if they ever would have analyzed these data sets to this depth. But it certainly was a lot of Python programming to get all that data, micron resolution, in the same box, so to speak, and then to do all of this, all the Python code. Do that had to be there. Data sets are terabyte in size, so you don't just manually. You have to tell Python how to go look. So it was tremendous.
Hi, I'm Dennis.
Where's the? Oh, there you are. Okay.
I'm JC's son, so he's always spoken very highly of you. Um, First of all, I just want to say that making like the UI for that like characterization, that's really awesome. Um, I guess I have two questions. First, on the question of like why the difference between the strength of additive manufactured tantalum versus normally machined tantalum. I just wanted to know like what are the biggest like mechanism changes that make the strength so different?
Oh, in the tantalum?
Yeah.
So, yeah, those were actually wire plate experiments, and we have 3D data sets that I didn't describe. And in the wrought material, the failure process was primarily void nucleation at quadruple points. Now the triple lines come together. Those would nucleate all the early voids, and then they would coalesce. In the additive material, you have all these columnar grains, and so you don't have those quadruple points. And so where actually most of that lower strength was a lot of these gains of high D&D density and completely different nucleation sites that led to failure. Then there's also, before you get to void nucleation, then there's
And then the second question, I had a lot of fun like plasma sintering and about equal compositions of niobium, moly, tantalum, and tungsten together. Um, but the process was like it was really slow because like the heat that was required to do that, and also like plasma that we tried to use it was like very small area, right? So
things that melt above
yeah,
3,000 C.
just thoughts about like
Yeah, so it's very difficult.
applications.
I think it's hard to convey. I think that it's easy to go look at a picture of four things, but it was melt above 2,000 C, and the other one is.
Okay. It was a wonderful talk. Thank you. I especially liked that your message from reaching for the stars. You need atoms to reach for the stars. So
I like that.
you're accomplishing, you're taking the smallest things that humans can achieve and using that for the largest things we can accomplish. So, congratulations on the lecture. I wanted to ask a question about the typing. It seems like you're quickly milling away a lot so that you can get the pictures, like if I get the message correctly. And I guess in the process you generate some junk. As
I
everywhere
always
inside the
wonder
chamber.
if somebody's going to ask that question. I intentionally leave it out because it's very good.
Where does the junk go? I mean, how do you keep it clean? Microscope.
When we started this, we had an old we shoot a hole in the wall and ruin the whole piece. But what we actually do is we take EPSD data, we put back to zero, and then we built a little cage on comes in from the backside of the microscope that basically surrounds the sample. And so all of the ablative material kind of lands on the inside of this little partition that we put around the sample. And then every once in a while, we have to go in and clean it. It's surprisingly durable. We really were not confident that practical problems like that we could some of the beginning. Told us it was impossible, so we tried it anyway. In fact, even after we showed some of the early results at a conference, somebody told me that they tried it and it wasn't possible. So, yeah, there's a lot of little tricks like that. And yeah, so what you really need is a lot of ports on your microscope.
Hi, Teresa. Wide-ranging talk. This has been amazing. But my question is about your high cycle fatigue data. So in the real world, that would be on something like turbine, right? Your aircraft spinning really fast for long periods of time.
Yeah, so in this case, because ultrasonic fatigue is so fast, that's why we picked it at 10 to 9. And in the real world, the blades, when you take off, you have vibrations that are in that frequency range, or a little bit less than that. Obviously, those don't persist for very long, or every turbine blade would just go away. Either
Because every
take
time
up
they
or-
launch, it's a low cycle fatigue,
Yeah,
much
so
higher
you get
amplitude, leaves everything out. And high cycle fatigue, or that's how I always understood it.
high cycle fatigue is just the airfoil vibrating as you take off. That is designed around. The blade is designed to resist that. Low cycle fatigue is really a thermomechanical fatigue. Usually, most serious chips on the trailing edge of the blade. What we haven't, that we don't have enough. Maybe we'll have to go back to it. We haven't done that same analysis for low cycle fatigue as we did for high cycle. Charlestonville is now in faculty at Illinois, still working on that, but requires a lot of longer LCF tests. That is where your question was going. I agree. There's there.
Well, I will tell you, that was a topic of my master's thesis, really long time ago. What we learned was that even though all this stuff was developed during the high cycle fatigue, every time the aircraft took off and landed, it would wipe the whole thing out with dislocation, clear it all out.
Except for the ones you didn't.
Well,
True.
today
It's
we
always
much better
true. I mean,
tools.
isn't that amazing? I mean, when you look at how many dislocations you have to reverse. Oh, am I really? If you look at this load unload cycle, here it is. I mean, every slip band that disappears there disappeared by the motion of what? Let's say light blue. So that's about 50 nanometers. That's about 200 dislocations in a precipitation strengthened material that ran back in the other direction. Kind of shocking, really. But clearly, there's a few places where they don't. And so those are the ones that matter.
Any more questions? Yes.
I had just kind of a more general question. You mentioned applying the machine learning techniques were not that useful if all of your data says that all of your materials are great, so anything you try
Correct,
can be great. How should we think about publishing data that is not so cool? Like, oh, we tried this thing, it was expensive, we put a lot of time into it, and it turned out to be a dud.
It's valuable data
Yeah. How do we think about that? And
in a table in the appendix, and it can be found and used.
Great.
I think that's the simple answer. We all need to get in the habit of doing that. What was the not so useful data, but it's still useful for other reasons.
We have a presentation to make to Dr. Teresa Pollock. Thank you so much for coming.
He's the boss.
Where do you want?
Well, you know what it is, yes. Or you can explain to us.